Boltzmann distribution is given with this equation or this formula, where A here is the normalization constant. So this one is the Boltzmann factor. We have the small letter k, the Boltzmann constant, equal to 1.38 times 10 to the negative 23 joule per Kelvin. So we convert this to electron volts. 1 electron volt is equal to 1.6 uh, 0218 to times 10 to the negative 19. So approximately this is equal to 8.617 times 10 to the negative 12 electron volt per Kelvin. The Boltzmann derived and explained the fundamental properties of the distribution functions for velocities of gas molecules in thermal equilibrium. And Maxwell really worked on the velocities of gas molecules in thermal equilibrium, but Boltzmann cured velocity distribution of gas or molecules, not in thermal equilibrium, would evolve into Maxwell distributions. The energy of gas is given by this equation. We have here the square of the momentum over twice of the mass. So mass times acceleration due to gravity. So this one is the uh, gravitational potential energy, and this one is the kinetic energy. So the total energy here is equal to the sum of kinetic energy and gravitational potential energy, or in short, the uh, total energy is equal to the square of the momentum over 2m. So here is the mass plus the gravitational potential energy. We have here U equal to mg z. We have the momentum equal to mv, mass times velocity. So by substitution here, so we have the uh, total energy here, sum of kinetic energy and potential energy. So we have this one, the energy over kT. Now, this is also equal to this one. If multiply both sides by dz, and our d sub 0 here is equal to this one, okay? Because this is the part, this part is equal to this part. Okay, then we are going to uh, normalize this one, to find the value of the normalization uh, constant. So we have here, so by normalizing this, we can find this d sub 0 equal to mg over dt. All right, so this equation, the Boltzmann distribution times dc. So this is the change in the z, and we have the d sub 0 uh, times e to the negative mg z over dt. So this is what we call the law of atmosphere. Okay, and in the law of atmosphere, we have the m here, the mass of an ideal gas in the atmosphere. So we have also the g here, the acceleration due to uh, gravity. So this one is acceleration due to gravity. So we have also the z here. Z is the vertical distance of the ideal gas from the ground. And the small k here is the Boltzmann constant, equal to 1.38 times 10 to the negative 23 joule per Kelvin. And the capital letter T here is equal to the absolute temperature in Kelvin. Now, the gas density at the ground is 1.292 kilogram per meter cube. So we have this problem. An ideal gas in uniform gravitational field at a molecular weight of 28.6 gram per mole. Compute its density at a height of 1.5 kilometer above the ground when the temperature is 300 Kelvin. So we have the given here. The molecular weight is 28.6 gram per mole. Convert it to gram. So we have 0.028 kilogram per mole times 1 over this is the Avogadro's number, this one. So we have the mass here, 4.25 times into the negative 26 kilogram. This is the mass of one molecule, okay? Then our z here is the vertical distance, 1,500. Acceleration due to gravity, 9.8 meters per second squared. The Boltzmann constant here, and the Kelvin temperature, 300 Kelvin. So the ratio of density at the height of 1,500 meter, at 1,500 meter above the ground, and the density at the ground is and the density at the ground is 1.292 kilogram per meter cube. Is equal to the ratio of uh, f of 1,500 over f of 0. Now we have here the Boltzmann Boltzmann uh, the, you have the Boltzmann distribution here function. So this is the distance from the ground, 1,500, and this is the Boltzmann distribution functions at the ground. So that is the density at the height of 1,500 from the ground over the density at the ground is equal to the distribution functions at 1,500 at the height of 1,500 meters over the distribution functions on the ground. So we substitute here using the Boltzmann distribution functions. So we have here. So our given here. No? So we have here the distance from the ground, 1,500. Acceleration to the gravity is 9.8. This is the Boltzmann constant. We have the mass here, 4.75 times 10 to the negative 26. We have the temperature in Kelvin. And we have the density at the ground. So we can substitute that here in the formula. Okay. So we have the okay. So this one. So this is what we are solving. Then we substitute the given here in this equations or formula. So what we have is let us enter now. So what we have is the answer is 1.0948 kilogram per meter cube.